Okay, so we wrote down, remember this nice dual formulation of our Kantorovich problem that we want to study. What we said, in order to learn more about this, obviously this is basically an optimization problem that we've written down, so we need to know a little bit about some of the key tools from optimization. So we're just backing up a little bit and doing some review of convex analysis just to make sure we have the language and the tools that we need in order to study this problem. But of course, afterwards, we're going to go back to our dual problem and see what we can actually learn about optimal transport from this. So one of the last things we wrote down last time was the definition of the subgradient. All right, so that was this object. We said the subgradient of u at x, right? This was the slope of all tangent lines or tangent planes, basically. So this was the set of all p such that u of y was always greater than this tangent plane, okay, for all values of y. Okay, so I want to do just a quick example of this because this example actually ends up being important later on. So let's say that the function I have is a cone. Okay, so this looks like this. Okay, almost everywhere it's differentiable. Remember, when something is differentiable, the subgradient is just single valued and matches the actual gradient. But obviously, at this point here, we don't have a gradient. So can we compute the subgradient? Let's try to find the subgradient of u. In particular, at the origin. Okay, so let's write down the definition. We're sitting at x equals 0, the origin, where the tricky things are going to have. And we need to find p such that, okay, so such that u of y, so that's root y1 squared plus y2 squared, is greater than or equal to u of x, which is 0, plus p dot y minus x, x is 0. Right? This is nothing but the magnitude of y. Okay, so what happens? If y equals 0, right, we need this to hold for all y. And we want to find the p's that ensure this holds for all y. If y equals 0, it's automatically true, right? So if y equals 0, this always holds. Okay. At y not equal to 0, we need basically p dot y divided by the norm of y to be bounded by 1. Okay, so no matter what p we choose, we're always going to have this be the case. For every p that we like, we're going to have p dot y divided by the norm of y. Right? This is always less than the norm of p times the norm of y. So p times y divided by y, which is the norm of p. So this is always less than this. That means as long as p is less than 1, right, we want to try to make sure that this thing is always less than 1. That was our condition over here. As long as p is less than 1, we're fine, right? So this always holds for p less than 1. Okay, and how do we make it tight? In other words, what choices of p or y would cross the threshold here where we get equality? Yeah, so if they're pointing in the same direction, exactly. So if p hat is equal to y hat, we get equality. Okay, equality means that if p is bigger than 1, right, I can always find a choice of y that makes this bigger than 1, right? So we better not allow p bigger than 1. Okay, so in other words, if p is bigger than 1, we can find y to violate the condition. To violate this condition. Okay, so p less than or equal to 1 always works. P bigger than 1 is not going to work for us. All right, so we're going to conclude that the subgradient we want, the subgradient consists of all values of p that made this true. Now it means that we can take any vector, right, any vector in R2 as long as it lies within the unit ball, the closed unit ball. Okay, so we're going to conclude that du of 0 is really just equal to the set of all p in R2 with norm less than or equal to 1. And this is nothing but really a ball of radius 1. So I'll call it a ball of radius 1 centered at the origin. It's a closed ball. Right, so if we want the subgradient of this thing everywhere, then what are we going to conclude? The subgradient is equal to this ball if we're at the origin. Okay, otherwise, we're in the regime where this thing is differentiable, so we can straight out take the gradient of this thing, and we're going to get that otherwise it's equal to x divided by the norm of x. Okay, so this is our subgradient, and we said we can talk about subgradient at a point. We can talk about subgradient on a set. So for example, I could talk about the subgradient of u over all of R2. Be the union of all of this. In fact, it's still just the closed unit ball. Okay, and this understanding this kind of weakened notion of differentiability is going to be important when we want to start looking at problems that have less regularity, where, okay, we said kind of formally we'd like maybe our optimal map to be the gradient of a convex function, but we know in reality maybe we don't have that much regularity. Relaxing things to use the subgradient lets us do different things, like say one point gets spread to a lot of points, like the unit ball. So this will actually be a key to interpreting Monge-Ampere if you want to have measures rather than densities. Any questions on the subgradient? Makes sense? Yes. Yes. So for x not equal to 0, it's just the gradient. Exactly, this is the gradient. All right, so if we do a quick derivative with respect to x1, say, 1 over 2 root this times 2x1, right? So you just get x1 and x2 divided by this magnitude. Okay, let's see what else we can do with convex functions. I'm going to motivate this a little bit with a 1D picture and then define things the right way. So let's think about f being a convex function. Let's just say it's in 1D for now. We're going to very quickly generalize this. Suppose f is convex on R or on some domain that belongs to R. Okay, so it's some function. And for now, I'm just going to assume it's kind of as nice as I need it to be. Now, what we're going to try to look at a little bit more is the slopes. Okay, we were looking at slopes here, right? Derivatives. So what you might notice is, say I want to find a point on this graph, on this curve. I could just do what I would normally do and say, okay, x is my independent variable, and I just travel along here, and I find my point. The other thing I could do is I say, I'm looking for a particular slope. And maybe I want to find a point on here that has slope 1. Well, that also uniquely, if things are nice enough, we have uniform convexity, identifying the slope also uniquely identifies where we are on here. So I might say here, the slope is equal to y is equal to 1. And that would be another way of identifying where I am on here. I could say, where's the slope equal to 0? That finds a point. Where's the slope equal to 2? That finds a point. So I could think of these slopes as my independent variable in some sense if I want to. Okay, so let's just draw a little picture of what's going on here. Here's my x. This is going to be my f of x again. Here's my convex function, whatever it is. I'm at some point x, or correspondingly, there's a slope y here. Okay, so here the slope of this is equal to y. This height here, of course, is f of x. Call this f of x. And then another natural height that comes out of here is the distance between here, the height of this tangent line, to where we intercept, say, the y-axis. Okay, what's that height equal to? Going back to our high school, whatever, what is this height equal to? Right, this distance is x. This is our run. We want to know our rise. We know the slope. Y times x. There we go. We made it there. All right, so this height is equal to y times x. Slope times distance. Right? There's nothing fancy or tricky about that. And then when I know those two heights, I can also get this height here. All right, it's just xy minus f of x. Okay, that's the y-intercept of this tangent line. Okay, so I'm going to call this g of y. So given x, fix x, I can create this new function of y. Right? And y is another way of thinking about my independent variable, we said. So let's, for fixed x, let's define g of y to be equal to xy minus f of x. Right? This represents basically the y-intercept of this tangent line. Okay, and there's a relationship between x and y here, right? We know that we said at the beginning y was equal to the slope. In other words, the derivative here. Okay, so let's see if we can clean up this condition a little bit. We've got this guy with a particular condition on how x and y are related. you could pull this condition out by taking a derivative of this with respect to x and setting it equal to 0. All right, so this extra condition can also be attained from differentiating g with respect to x and setting equal to 0. Okay, so another high school calculus question. When do we usually differentiate things and set things equal to 0? What's that? When we're optimizing. Yeah, when we're trying to maximize or minimize things. So this looks like a lot like optimizing. So maybe, right, maybe when we're trying to find the right x to put in here, it's just the x that either maximizes or minimizes this expression. So maybe g of y looks like either the max or the min over x of this expression. Right? Because if we max or min this, we say let's take the derivative with respect to x, and we're going to end up with y equals f prime of x, the value of x that makes that true. Should we maximize it or should we minimize it? You want to minimize it? Why do you want to minimize it? We know f is above the line. Okay, so we want to minimize what, f? We want to minimize, yeah, okay. So in other words, we want to maximize it. Right, so f, what I've drawn here is a convex function, right? When we're doing optimization with convex functions, we usually like to minimize them, right? We can find minimizers under mild conditions. So this is something that looks like we'd like to minimize it. This we've got the negative of it plus something that's linear. That's probably something we want to maximize because that's concave now. Okay, so f is convex. That means xy minus f of x is concave. It makes sense to maximize it. Okay, so I'm going to propose that this object, g of y, that I've defined to be now, say, the maximum over all values of x, of xy minus f of x, may be interesting. Right, graphically, it says something about these y-intercepts. We know, writing it like this, that we get kind of an interesting connection between the x that maximizes this and the y that we care about, right? Somehow one is the derivative of the function. So people who have taken convex optimization, this should look familiar. Okay, you're nodding. So a little bit more detail. How does it look familiar? It's the Legendre transform, exactly. So this is just a little graphical picture of where the Legendre transform comes from. I always think that people just write it down. Let's try to look at this random object, and maybe it'll be interesting. This is just a little picture of where it comes from. So let's define the legendre-fenchel transform of a function by, denoted by f star of y. Okay, and this is going to be the supremum over all values of x in whatever domain I'm living in. All right, if I'm heading into Rn instead of just the real line, I'm not going to do a product here. I'm going to do a dot product. x dot y minus f of x. Okay, and somehow we have reason to expect that the x that actually shows up in this supremum or maximum will somehow be related to the gradient maybe of f, maybe the subgradient of f if we try to generalize this. But this is going to be an important object. Okay, so just for a couple quick examples. This is probably the dumbest, simplest function I can think of. I need a domain. So let's let the domain be everything. Okay, then f star of y is going to be, okay, the supremum of x in R of x dot y, that's x times y in 1D, minus f of x, which is 0. Okay, and now it matters what value of y I've put in here, right? If y is 0, this is 0. So this is 0 if y is equal to 0. If y is not 0, this is unbounded, right? So in fact, this Legendre transform has a very small domain. This domain is a point. So I'm going to say the Legendre transform of this guy is equal to 0, but the domain of f star in this case is just a singleton. On the other hand, if I changed up my domain, same function, different domain, okay, just pick an interval. Now my f star y is the supremum, okay, again of x times y minus 0, not for x in R, but for x in this interval. And now what's the best I can do here? If y is positive, I pick x to be positive 1. That's the maximum I can get. If y is negative, I pick x to be minus 1. That's the biggest I can get. This is now equal to the absolute value of y. Okay? And now the domain is anything. Okay, so the domain of f star is everything. And of course, you can do many other examples, which I assume that you can work through. This one I'm going to write down, but not do it. If f of x is a linear function, p dot x, then if I do a Legendre transform, and then I do another Legendre transform, I get back where I started in this case. Okay, I'm not going to work that out for you. You can work that out for yourself if you want. What's that? It is true for any convex function, yes. Yeah, so this is sometimes called the convex conjugate also, when you take the Legendre transform. All right, that's my Legendre transform. Now we need to know more properties than just how to compute a few toy examples. We want to know some key properties that we can actually use in trying to build up some kind of robust optimization theory. Okay, so I've already hinted here. Once we take a Legendre transform, you can take Legendre transforms again. So we can certainly take repeated Legendre transforms, or LF. I'll write LF sometimes for legendre-fenchel transform. Okay, and this is also called the biconjugate of F. Okay, so what do we need to know about these things? One property of them. I'm going to list a bunch of properties of the Legendre transform. Some of them I'll prove, some of them I won't. But I want to give you an idea where this all comes from. And one is that when we take these Legendre transforms, we get a convex function. Okay, so check this. We just use the definition of convexity, right? We say, let's pick any y1 and y2 that I'm allowed to plug into this thing, and pick some lambda. Okay, f star of lambda y1 plus 1 minus lambda y2 is equal to the supremum over all x of, okay, now we're going to have x dot y, this is my y, so lambda x dot y1 plus 1 minus lambda x dot y2 minus minus f of all of this. Right? So this is what I take the supremum of. X dot y minus f of x. So this is my y. F of x is simple. And now I can break this up a little bit. Right? I could think of this as lambda times f of x plus 1 minus lambda times f of x. So I have the supremum of a whole bunch of things. If I try to maximize them individually, right, this is going to go up. So this is the supremum bounded by the supremum over all x of lambda x dot y minus lambda f of x plus the supremum of 1 minus lambda, that's x dot y1, x dot y2, minus 1 minus lambda f of x. Okay, now each of these look like a Legendre transform, scaled by lambda or 1 minus lambda. Okay, so this is nothing but lambda times f star of y1 and 1 minus lambda f star of y2. And that's convexity. Okay, so whatever we start with, once we take a Legendre transform, we've got a convex function in our hands. Another interesting property was the one we sort of started with when we motivated this a little bit, was to say there's some sort of connection between the x and the y that show up here, right? Somehow one is related to the derivative of the other one. Right, we're playing with convex functions. I don't want to assume everything is differentiable. We know we need to be able to weaken that, but we have this concept of the subgradient that we can write down. So here's another useful property. Okay. Property. If x is in the domain of f, and y is in the domain of f star, then two things. We've got an inequality, and we've got conditions that make it tight. So first of all, f of x plus f star of y is always greater than x dot y. Oh, there's nothing to prove there. That pops immediately out of this definition. So what's interesting is when we get equality. Okay, with equality, if and only if y happens to be an element of the subgradient of f. Okay, again, if, when we started and we said everything is differentiable and nice, that's precisely what you'd expect if we're maximizing this. We expected that y should be equal to f prime of x. That would give us the maximum. But now we're saying actually we can generalize this a little bit, and this works for y belonging to the subgradient of f. And there could be, this is a set valued thing, so there could be more than one value of y that makes this true. Okay, so why does this work? Okay, so the inequality is immediate. There's nothing to do there. Okay, now what I want to do is start with some y that belongs to the subgradient and show that's equivalent to getting equality here. Okay, so let's choose y living in this subgradient. Okay, so let's just write down what that means, right? We have a definition of the subgradient. So this is true if and only if. This is an equivalence. I need another variable. Let's go with z. So f of z is greater than f of x plus, okay, now I don't have p. Y is the element of my subgradient. So plus y dot z minus x. And this should be true no matter what value of z I put in here. Okay, we can rearrange things a little bit. So in particular, I want to rearrange things a little bit to get terms that look like the terms that come up when I do Legendre transforms. So terms that I get when I do Legendre transforms would be something like an x dot y minus f of x. So let's pull that over here. So x dot y minus f of x is greater than or equal to z dot y minus f of z, no matter which z you choose. Okay, if this is true for all z's, it's also true if I take the supremum of this over all z. Right? And that's also an equivalence. So I could say x dot y minus f of x is greater than the supremum of z dot y minus f of z. This we should recognize, right? This is the Legendre transform. This is f star y. Okay, so what have I got? If I rearrange this a little bit, I have f of x plus f star y is less than or equal to x dot y. Okay, and again, this was all equivalent to the fact that I chose y as an element of the subgradient. Okay, so this is now true in this case. And I see your eyes all darting over here, which is good. That's where they should be darting. You're calling that this is automatically true no matter what x and y I pick. So combined with the opposite inequality that we always had. Okay, for all choices of x and y, we get the equality. Okay, so we started by motivating with the simple, smooth 1D example, but what we did there really goes through. That if we have things that are not differentiable, we can still make this nice connection between the subgradient and the point that we care about. Okay, another useful property that we're going to need happens with functions that are ordered. But somehow taking Legendre transforms, preserves, or actually reverses ordering properties. So if f is less than or equal to g everywhere in the domain, then g star is less than or equal to f star. Okay, this is a one-liner. Right, we have something where we've got x dot y minus f of x, and if we know there's an ordering between f and g, then the ordering goes through. Well, it's a one-liner, and if you don't believe me, you can work it out yourself. I'll entrust that to you. Okay, so now this is a property that has already been pointed out. If we are in particular working with convex functions, then by taking the Legendre transforms, if we do it twice, we get back where we started. So this guy is important. Okay? If f is convex and lower semi-continuous, then the Legendre by conjugate is equal to the original function. Okay, so I'm going to at least sketch out why this is true. So what do we know? First of all, we know that f of x plus f star y is certainly bigger than or equal to x dot y. Okay, we wrote that down already. That means if we look at the biconjugate, this is the supremum now over all y of x dot y minus f star y. Okay, x dot y minus f star y is less than f of x. Doesn't matter what value of y you put in here, so this is automatically less than f of x always. Okay, so what we want is to try to get the equality happening here. Okay, so here's where I'm going to sketch things out. I'm going to take my function f and say it's convex. That means I can represent it as a supremum of a bunch of hyperplanes. Okay, so f is convex. I can draw all these different supporting hyperplanes. This one, and this one, and this one, all of them. And if I write all of these supporting hyperplanes always stay below f, and if I take the supremum of all of them, right up until the boundary, the supremum of all of these things is going to give me my function. Okay, so And here is where I'm not filling in all the rigorous details of why I'm allowed to do this. That's why I call this a sketch of the proof. Let's represent F as a supremum of a bunch of hyperplanes. Okay, so in other words, f of x is equal to the supremum over all alpha in some set, whatever it is, of L alpha of x, where each of these L's is one of these hyperplanes. Okay, and I want to use that to try to reverse this inequality. Right? This representation is specific to the fact that we have a convex function. Okay, so let's choose any of these allowed alphas. Alpha's just been used to index all of these hyperplanes. Okay, and what do we know? We know that f is always above the hyperplane. This is true for all x. All right, so if we have ordering of these two functions, we have ordering when we take Legendre transforms. So we have f star of y is less than or equal to L alpha star. And let's keep going. We're trying to get to a double transform. So f double star. Did I reverse the inequalities? Where? Here?
Yeah. F is greater than L.
F is greater than L, yep.
Right, so by that property up there,
It reverses every time you do it, yeah.
it reverses every time.
Right? So F is less than G, so F star is bigger than G star, yes. So indeed, I reversed the inequality, and I think I meant to do that this time.
Right.
But yes, point these out because sometimes I will reverse them without meaning to. I can tell you that until some of these technical results, I've spent in an hour standing at the whiteboard with the collaborator going through all these inequalities, and an hour later we realize, oops, they're all facing the wrong direction. We've got to start over and see if this reasoning still works. So yes, please point out if you think I reversed things. Okay, so now I'm going to reverse the inequality again, and I get L alpha double star of x. Okay, this I kind of wrote down as a, you can check this on your own time before. I said if we have a linear function and we take a double Legendre transform, we get back where we started. Okay, this is not quite linear, this is an affine function. Again, I'll let you check that. It's a relatively simple exercise that if I take one of these hyperplanes and I Legendre transfer it and I Legendre transfer it again, I get back where I started. All right, so for a generic function, it may or may not be easy to check that property, but for an affine function, it's not so hard to check that property. So we get right back where we started. Okay, so since L alpha is affine. Okay, so this is always true. I should just choose any one of these hyperplanes. I don't care which one. This property goes through. And that means if I take the supremum of all of these hyperplanes, this property still holds. So we have the double Legendre transform of f is also bigger than or equal to the supremum over L alpha of L alpha of x. And that's precisely how I represented my convex function initially. Okay, so what do I have? F double star is bigger than F. F double star is less than F, right? This property always holds. It doesn't matter what F is. This property only holds for convex F. Therefore, we're going to conclude that F double star is indeed equal to F. So if you have a convex function, you do a double Legendre transform, you get back where you started. The lower semi-continuous part came in here. What's that? Oh, how do you mean a more general space where convexity doesn't apply?
It doesn't imply this lower semi-continuity.
It doesn't imply lower semi-continuity. No, because things can go crazy at the boundary. So convex functions in the interior of the domain or on open sets are continuous. Once you get to the boundary, all hell can break loose, and you can get very, very weird things happening. And that comes because convexity comes from drawing a line between 2 points. But when you're sitting on the boundary, you draw a line between 2 points, and now those points are on the boundary. You're never going to run through those points, essentially. So they're allowed to do strange things. They're allowed to jump way up, whatever. Okay, so if I just sit around and grab a function and start taking Legendre transforms over and over and over again, eventually I'm just going to have two functions that I keep alternating between, right? Maybe I start with a weird function. I take a Legendre transform once. Now I've got a convex function. Take another Legendre transform. Now I've got another convex function. So if I do another Legendre transform, I'm going to get back to my earlier convex function, to my next convex function, and so on. So you start with any function, and there's really only two functions that I'm going to end up caring about. And that's important. That means I'm going to refer to these two functions as a Legendre-Fenchel dual pair, and it makes sense to talk about these things coming in pairs. They're these pairs that I would be alternating between. So with this property, it's now reasonable to talk about convex Legendre-Fenchel duals. Okay, so say phi and c. Okay, such that these guys are Legendre transforms of each other. So such that phi is c star and c is phi star. Right? And this makes sense, right? You give me a convex function phi. I take its Legendre transform. I get another convex function. I take its Legendre transform again. I should get back where I started. So this is perfectly reasonable. Yes, we're happy with this. Okay, one more property that we might want is if phi of x and c of y are dual functions on bounded domains, capital X and capital Y, then we can come up with uniform Lipschitz bounds on these functions. That shouldn't be surprising to you from what we've talked about so far, is that somehow the elements of this set that live in the Legendre transform should look like gradients or subgradients of the functions we started with, right? And similarly, vice versa, right? Somehow the elements in here should look like subgradient values of one of these other functions, okay? So if x and y are bounded sets, then somehow we're expecting these subgradient values to also live in a bounded set, okay? And if our derivatives are bounded in some sense, then we expect Lipschitz bounds. Okay? I could argue that more precisely. So this is the kind of object that we need to look at, phi of x1 minus phi of x2. Right? We would want to bound its absolute value by something times x1 minus x2. Okay, so this is the supremum over all y of, okay, this is a Legendre transform of C. So x1 dot y minus C of y minus, and again, it's a Legendre transform, x2 dot y minus C of y. Okay, I don't know a priori if this supremum is actually attained as a maximum, but I know that I can get arbitrarily close to this value, right? So you give me any epsilon that you like. I can find, so for any epsilon, we can find, say, a y1 such that all of this minus phi of x2, we might not hit the supremum, but we'll get within epsilon of it. So is x1 dot y1 minus C of y1 plus epsilon. Right? I can always get arbitrarily close. I can get within epsilon. On the other hand, if I plug y1 into here, okay, we're less than the maximal value. But since there's a negative sign in front of that, that works with the inequality that we're doing here. So I can write x2 dot y1 plus C of y1. Okay, and then things simplify a little bit. What do we get? We get x1 minus x2 dot y1 plus epsilon. Okay, this we know we can get bounds on. This is bounded by the norm of this times whatever the biggest value this might ever take on in magnitude is. This is constrained to live in some bounded set y. Capital Y we said was bounded. That's important. So this is less than or equal to the supremum of all y values times x1 minus x2 plus epsilon. Right, that works for any epsilon, right? So I can take epsilon to 0, and I still have this inequality in the limit. Okay, so taking epsilon to 0, what do we get? We get that phi of x1 minus phi of x2 is less than or equal to some constant times x1 minus x2. Okay, there's nothing special about the order I did these in. I could have done them in the other order, phi of x2 minus phi of x1. I would have gotten the same thing with exactly the same constant here. Okay, so similarly, we get bounds on the magnitude. And same thing for C. Okay, so in the end, we're going to get phi and C are uniformly Lipschitz. Any questions there? This was a very brief foray into some topics from convex analysis, which, as you know, you can take whole classes on. So we've not done everything by any means, but we've got, I think, the basic tools in place that we're going to need to start talking about optimal transport and start proving some things. Okay, so let's try to go back to the problem that we care about. The problem, where we left the problem that we care about was we wrote down this dual formulation. And we said, okay, it looks kind of reasonable, right? When we did it with Dirac masses, then we said, okay, then the problem looks like your traditional finite dimensional linear program. We have a dual formulation. We wrote down a similar dual formulation for the more general problem, but we weren't quite sure what to do with it from there. Okay, so let's come back to our dual problem. I'm going to focus on quadratic cost. I think later we'll try to see what happens when we generalize the cost, but you need new notions of convexity to do that. Okay, so what was our dual problem? Our dual problem was to try to maximize. Okay, so in very abstract notation, right, we were looking for a pair of functions belonging to some feasible set, and then we were trying to maximize some objective function. Okay, and I'll just remind you what this was. This was going to be the integral of u with respect to our source measure plus the integral of v with respect to our target measure. All right, now we have some tools from convex analysis. We want to study this. This is probably not written quite the way we'd like it to be to use tools of convex analysis, because usually when we're doing convex analysis, convex optimization, we're saying here's something convex and I'm going to minimize it. Right now I have a problem where I'm trying to maximize something. That's no biggie. We just have to take these things and flip them upside down, and then we can start minimizing. So since we want to use some tools from convex analysis, let's transform these variables a little bit. So instead of u and v, I'm going to do something like minus u and minus v. Okay, so instead of u and v, I'm going to have phi and psi. Phi of x is going to be, leave a little space here, something like minus u. And psi of y is going to be something like minus phi. Because if we're trying to minimize this with, or sorry, maximize this with the u's, then hopefully we're trying to minimize it over the ph's and c's. What I'm going to put here, and it's going to be clear in the next line how this simplifies things. I'm going to put here a half x squared. Again, in the very next line, you'll see where this just lets things cancel out. It doesn't fundamentally really change anything, but it just cleans things up a little bit. And here a half y squared. Okay, so instead of maximizing j, we try to minimize minus j. It's the same thing. Right, which is minus u d mu and minus v d nu. Okay, minus u is the same as phi minus half x squared. And this is going to be the same as c minus half y squared. What's that? Is it a plus for the y? It's a plus, yes, thank you. Okay, so I could minimize this, but also this half x squared here, this doesn't change anything, right? This isn't affected by phi at all. So it doesn't matter that it's here. It doesn't matter that this half y squared is here. So we could leave those out and say, or just minimize this thing. Right? If we've managed to minimize this, then we've managed to minimize this plus a constant, because we don't get to change the constant. Okay? And this, I'm going to, again, give a name. In fact, it's no different than the j that we started with, except now we're minimizing it instead of maximizing it. All right, that's my new objective function. Then we also have constraints. The good thing, again, is we're minimizing this, which makes sense when we're trying to do convex analysis. But what are our constraints? Okay, so we had a constraint that said, remember, u plus v was less than or equal to the cost function. So here my cost function is quadratic, half x minus y squared. And that provides an upper bound on u plus v. Okay, and now we say, well, we don't want to work with u and v anymore. We want to work with these guys. Okay, so u is going to be equal to half x squared minus phi and a half y squared minus c. Okay, and hopefully it starts to become clear why I decided to add these extra half x squared and half y squared in here. All right, if I multiply out this side, I get a half x squared, which could cancel with that. I get a half y squared, which can cancel with that. And then my cross term, minus x dot y. Okay, so there was nothing really fancy in deciding to put these in here. It was more about starting with a minus phi and a minus c, and then saying, well, actually, if I just added this extra little bit here, it just makes things simpler. I have a cleaner constraint to write down. This is no biggie. There's no magic there. OK, so what's my actual constraint? My actual constraint is going to be phi of x plus c of y. Move them over. This is a minus x dot y that I've got left over. So that comes over here and becomes x dot y. Okay, so I gave shorthand for this. I'm going to give shorthand for my constraint set to just not have to write it every time. So I'll call it phi star. And this is going to be the set of all phi and c that are continuous functions and that satisfy this constraint. So such that phi plus psi is bigger than x dot y for all x and y. Okay, so abstract notation. Our new problem is which I'm going to call, okay, dp star. It's the dual problem, and I just tweaked it a little bit. I turned it on its head. So this is going to be to minimize L of phi psi over phi and psi living in my new constraint set. Any questions on this so far? Right, so I've taken the dual problem that we looked at the last class or two, and all I've done is turn it on its head a little bit just so this looks like something that we might be able to study using tools of convex analysis. We're in this nice situation where, right, phi and psi are our unknowns, and they show up in a linear way here, so this is good, right? When we wrote down our original primal problem, a Cantor-Ovich problem, everything is kind of nonlinear. But here we've got simple conditions, we've got simple constraints, it's all very linear. Now, what can we do with it? Can we study it? Can we show that we can minimize it? And can we maybe hopefully learn something about the structure of the minimizers and how they relate back to maybe coming up with transport plans or transport maps. First question that we always have to worry about when we're doing an optimization problem is the feasible set not empty? So the feasible set is this guy. Let's say, can I find functions that live in this set? I see a nod, so give me an example of such a function. Any function in its dual? Okay. Like, give me one really simple example. 1 over px to the p? Okay, how about an even simpler example that everybody's going to believe? We're in a bounded domains, right? That means there's bounds on what this value can take, right? This has a maximum. So let's say the maximum of x dot y is 1,000, whatever. I could just say, let's let phi of x be a constant function equal to 1,000, and psi of y is a constant function equal to 1,000, and now boom, this is satisfied, right? So this is not quite trivially, but almost trivially non-empty. But of course, you're recognizing in here that this looks a lot like things that come up with Legendre transforms, right? If I move this over here, x dot y minus c, that's exactly the kind of thing that we expect to see when we're computing a Legendre transform of c. And indeed, we're going to see that. So the feasible set is certainly non-empty. Okay, just take large constant functions. Okay, so let's think a little bit more about what the minimizers might look like, what the feasible pairs might look like. So let's try to understand what kind of functions we're actually working with here. Okay, so what feasible pairs actually look like. Okay, we've just said there's a connection somehow with Legendre transforms. They feel like they're going to come up naturally here, so let's try it. Let's start with a feasible pair. Okay, we know right away that this is true. Phi of x is bigger than x dot y minus c of y, always. And that means it's also true if we take the supremum of this side, right? Which is exactly a Legendre transform. So that means that phi of x is in fact bigger than or equal to the Legendre transform of phi. Okay. What else do we know? I'm just going to write down a couple of properties that we've already talked about with Legendre transforms and just record them here so that we can use them in a minute. So we also know that c of y, right, is bigger than or equal to c by conjugate. This was always true, right? The other way around only worked if c was a convex function, but this way was always true. And we know that this is always true. So if we take a function and its Legendre transform and add them up, this was always bigger than or equal to x dot y. Okay, so I see your eyes drifting back over there. And what are you seeing over there that's useful? You're seeing the constraint, exactly. So I started with a feasible pair. This pair, phi and c, satisfies the constraint. Worked down a little bit. Now I'm seeing my constraint pop back up again. But it's not phi and c that are sitting here anymore, right? It's these new functions, c star and c double star. They also satisfy the constraint. So if I start with a feasible pair, I can build a new feasible pair, always. Okay, so we have a new feasible pair. Okay, so we'll call c star and c double star, right, which is a Legendre dual pair. Now my claim is, okay, we know that feasible pairs don't have to be Legendre duals. They can, as in this case. They don't have to be, as in the case of just taking large constant functions and sticking them in. What I claim is that we don't have to minimize over everything in this set. We could actually just restrict our attention to Legendre dual pairs. We can assume that the minimizers are Legendre duals. Okay, how am I going to do that? I'm going to say, let's start with any feasible pair that you like. Now I claim, and this will come up with some cost, right? We plug this into our objective function and we get some value. Now I claim that I can always reduce that value using this pair instead. Okay? So whatever this is not optimal. You can always find something lower that are Legendre duals. So let's look at the objective function. Okay, so what's our objective function? Our objective function is L, and now I'm going to try to put in this new pair, and I want to try to show that it reduces the cost as compared with the pair I started with. Okay, so C star, C double star. Okay, this is an integral of C star and an integral of C double star. Okay, I recorded a few inequalities over here because I said they might be useful in a minute. Here's where they become useful. Phi star is always less than or equal to phi, right? And C double star is always less than or equal to C. Those are just properties of Legendre transforms. So that means I can always bound this by, this I said was always less than C. This was always less than C. Okay, and this is, again, my objective function, but with the pair I started with. So what does this mean? If phi and C do happen to be optimal, that's great, but I can find another pair that's also optimal and are Legendre duals, or else they're just not optimal at all, and I'm wasting my time looking at them, right? So this is my conclusion. I don't need to look at all possible functions that satisfy my constraint. It's fine to restrict my attention to things that are Legendre duals, right? The minimum, if it exists, we don't know yet if it exists, but if it exists, the minimum will always be attained by a Legendre dual pair. And maybe it will be attained by other things too, that's fine, but it will also be attained by a Legendre dual pair. So this is our conclusion. We can minimize over this set. Okay, let's call it phi double star. So this is going to be all functions phi and C that satisfy my constraints, but also that are Legendre duals of each other, such that phi is C star and C is phi star. If there's a minimizer, I'm perfectly free to assume that it takes this form. These I can write as duals of each other. And that's nice. Now we've got a lot of structure. We can start talking about, with these minimizers, we can start assuming they're convex functions. We can start talking about their subgradients. We can start relating their subgradients to each other. That starts to give us a lot more structure to work with. So I'm leaving it there for today, but this is where we're going next class. Now that we've rewritten our dual problem, we're in business to really start using some convex analysis to learn a lot about the minimizers.